Greetings to respected madams, sirs. My name is Pavan Sai. I'm from CSE AIML. Today my presentation is related to the topic simulation of multi-tier circular queues for real-time task scheduling in Python from the course of data structures. And this is my format of the presentation. The content I'll be explaining. First, I'll be starting with the abstract, the problem statement, and I'll be introducing to my presentation and the requirements, prerequisites, technologies used, and the literature review and the methodology and conclusion. So, abstract, real-time systems require predictable long latency scheduling of the tasks with different priorities. This project implements and stimulates a multi-tier circular queues scheduling in Python to manage tasks across multiple priority level with which while maintaining zero NQs and DQs performance and boundaries latencies. The simulator demonstrates how tasks are scheduled, how priority against prevents starvation, and how the structure performs under realistic workload. And the result shows improved throughput and predictable responses time compared to a single queues approach. And these are the main sections. I will cover the abstract problems. So in the abstract, the real-time systems need efficient task scheduling. Circular queues offer fast, predictable operators. The multi-tier scheduling improves priority handling. Python simulates the to test behavior, and the project focuses on improving real-time task scheduling using a multi-tier circular queues. The idea to simulate how tasks are different priorities can be managed efficiently with predictable execution time. The problem statement. So existing scheduling struggles with priority handling. Single queues create delay and need faster, fair scheduling for real-time application. In many real-time systems, such as operating system scheduling or robotics, tasks are different priorities complete. A single queue structure increases waiting time and leads to priority inversion. The project solves the using layered circular queues, and the transitional single queue scheduling struggles to provide both priority separation and constant time operations, which are needed for real-time constraints. We need a scheduling structure that maintain fast NQ DQ of O multiplied by 1, supports multiple priorities tiers with fair service, no starvation, allows priority again, and preemption policies can be simulated and analyzed easily in Python. The goal is to implement and evaluate a multi-tier circular queues for real-time task scheduling. And the introduction. Um, so, slide content: what is circular queues and what is multi-tier queues? Application in operating system scheduling and embedded systems. A circular queues uses a warp around structure which avoids shift elements, but when multiple priorities exist, a single queue is not enough. So we introduced multiple tier high, medium, and low priority, each with circular queues. A circular ring queue is ideal when constant time queues, operations, and fixed memory footprints are required. Multi-tiering partitions tasks into priority level. Example: high, medium, low. As I talked before, explained before, with dedicated ring buffer per tier. Scheduling pools tiers for highest to lowest using egging and time slice policies to ensure responsiveness and fairness. This approach is common, which is in embedded and real-time operating system kernels, where it is predictable. It is where predictability is crucial. The requirements. Um, The requirements are Python and basic understanding of queues, real-time scheduling knowledge, input tasks with priority, plus burst time. For stimulation, I use Python 3, and the only required inputs are the tasks along with their priority levels, and simulate various tasks, loading and arrival patterns, periodic, sporadic, bursty. Implement multi-tier circular buffer with fixed capacity per tier, provided NQs, TQs, peak is full, is empty in O1. Supportive priority egging, preemption and configuration time slices. The prerequisites are queue operation, NQ, DQ, and circular queue logic, priority based scheduling, time slice based execution. To understand this model, knowledge of queues, operations, and time slicing is necessary since we stimulate a CPU like behavior. So, the basic data structure: queues, arrays, circular buffers. Concept in real time scheduling: priorities, preemption, egging, deadline, Python programs, programming classes, lists, threads, or asyncs for simulation. Basic statistics for performance analysis is mean percentiles. The technologies used are Python, lists for queues implementation, loops for simulation, and the time modular, which is optional. Also, I chose Python because it is simple and easy for simulation. List data type is used as the core queue structure. Python 3.3x core implementation, standard libraries, collection time, heap optional, random threading, async queue. Matplotlib, Seaborn for plotting results, latency, throughput. Jupyter Notebook for interactive simulation and visualization. And the optional technology is simply SIMPy for processing based discrete event simulation, and time modular time module is also optional. So I chose Python because it is simple and easy for simulation. Like data types, it is used as the core queue structure. And coming to the literature reviews, uh, the model is inspired by class scheduling techniques like round robin and multi-level queue scheduling. This helps in balancing fairness and priorities. In this slide, the standard scheduling algorithms, round robin, priority scheduling, multi-level queues are researched on real-time queuing and egging techniques to avoid starvation. Kernel schedules design like Linux CFS, patches for inspiration on fairness and preemption, paper comparing multi-queue versus single queue performance in embedded systems. And the methodology, the multi-tier circular queues embedded fairness within a tier and priority difference between tiers, the scheduling cycle throughout the tasks without wasting time on empty queues. So users sends a tweet contacting assembly instructions. The backend receives the tweet via Twitter API webhook. The initializations are parsed on and tokenized. Hazard detection, such as raw, var, and wow, where raw is read after write, var is write after read, wow is write after write. So the branch hazards, pipeline scheduling logic applies stalls forwarding. A pipeline diagram is generated, cycle versus stages. Final diagram is sent back to the user as a reply tweet, log and stats, stores for monitoring. And the results, multi-tier circular queues maintains O1 operations and low scheduling overhead under mixed loads. High priority tasks experienced significantly lower response time versus single queues. Round robin egging prevents starvation. Low tier task promotion, if waiting beyond threshold, deadline missed decreased when using appropriately. Turn time slices and capacities. Visualizations, plots of response time CDF, queues occupancy over time, deadline missed trend. Limitations are like fixed capacity can still cause drop under extreme bursts unless overflow policies are used, and simple egging adds overhead parameter using turning it into requirements. This is the small part of code in which I mentioned a class called circular queues, and I defined it with self and size, and self dot queue which is equals to brackets. So I defined enqueued and dequeued, and this output I got is the small part of code shows how queues and implemented which are implemented. And the conclusion, the multi-tier circular queues improves real-time scheduling, efficiency and fairness. The Python simulation demonstrate its efficiency. Overall, the model is efficient, simple, and subtable for real-time applications. And the advantages are fast on operation, priority preserved, less wasting time, good and real embedded systems. The simulation shows the multi-tier circular queues preventing starvation and ensure predictable execution. The multi-tier circular queue is an effective low overhead structure for real-time scheduling, and the balanced priority handling and constant time operations. When the combination with egging and proper time slice, turning it yield predictable, latency improved throughout for high priority tasks, and reduced deadline misses, and making it suitable for embedded real-time systems. Thank you.